In this lesson, we will apply the differential form of the conservation of mass and conservation of linear momentum equations to analyze a simple type of flow called Couette flow. Here we have a Newtonian fluid that is between two large plates. The bottom plate is fixed and the top plate moves to the right at a constant speed, capital U. The spacing between the plates is a distance b. Our axes are oriented so that y is positive toward the right, x is positive out of the screen, and z is positive upwards. We will assume the plates' lengths in the x and y directions are much larger than the gap distance b, so the plates can be approximated as infinitely long in the x and y directions. The gravitational acceleration g points in the negative z direction, and the bottom plate is located at z equals 0. We want to analyze the flow between the plates under the following conditions. The flow is steady, which means the velocity field does not change in time. The flow is incompressible and isothermal, which means the density ρ and absolute viscosity μ are constant. We also will assume the flow is laminar. Under these conditions, we want to determine the velocity components u, v, and w everywhere between the plates. To accomplish this, we will use the differential form of the conservation of mass and conservation of linear momentum equations, which are called the continuity and Navier-Stokes equations, for a rectangular coordinate system. The continuity equation for these flow conditions is partial u partial x plus partial v partial y plus partial w partial z equals 0. The Navier-Stokes equation in the x direction for these flow conditions is density times the quantity partial u partial t plus u partial x plus v partial u partial y plus w partial u partial z equals density times the gravitational acceleration in the x direction, gx, minus partial pressure partial x plus mu times the quantity second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to z. The Navier-Stokes equation in the y direction is density times the quantity partial v partial t plus u partial v partial x plus v partial y plus w partial v partial z equals density times the gravitational acceleration in the y direction, gy, minus partial pressure partial y plus mu times the quantity second derivative of v with respect to x plus a second derivative of v with respect to y plus a second derivative of v with respect to z. And finally, the Navier-Stokes equation in the z direction is density times the quantity partial w partial t plus u partial w partial x plus v partial w partial y plus w partial z equals density times the gravitational acceleration in the z direction, gz, minus partial pressure partial z plus mu times the quantity second derivative of w with respect to x plus the second derivative of w with respect to y plus the second derivative of w with respect to z. These equations govern how fluid will behave between the two plates, and solving these equations will tell us the velocity at every point in space. We can greatly simplify these equations by applying the assumptions already mentioned and using our intuition about how the fluid should behave. One of the assumptions is that the flow is steady, so the terms with time derivatives disappear. Next, let's think about the possible directions of the flow. Since the top plate is being pulled to the right, and it is the shear stress produced by the plate that is driving the fluid should only move in the positive y direction. Therefore, the only velocity component that is non-zero should be v, and the velocity components u and w are 0. Any term with a u or w can be eliminated. Next, let's focus on the velocity component v. Looking at the continuity equation, partial v partial y is 0. This means v is not a function of y. Additionally, there's no reason to think that v should change based on its x location. That is, as we move into or out of the screen, the value of v shouldn't change. But what about the z direction? Well, we have the no-slip boundary condition that applies at the top and bottom plates, and this means the flow in the y direction should be 0 at the bottom plate and capital U at the top plate, which means v does vary in the z direction. So we are left with the conclusion that v is only a function of z, and we can eliminate all terms that contain a derivative of v with respect to x, or a derivative of v with respect to y. Finally, we note that the gravitational acceleration acts only in the negative z direction. So gx and gy are 0, and gz is negative g. Let's clean up these equations. We've already discussed how the continuity equation informed us that v is not a function of y. The Navier-Stokes equation in the x direction simplifies to partial pressure partial x is equal to 0, which simply means that pressure is not a function of x. So pressure does not vary as we move into or out of the screen. The Navier-Stokes equation in the y direction becomes 0 equals negative partial pressure partial y plus absolute viscosity mu times the second partial derivative of v with respect to z. Here we need to use some intuition to simplify the equation further. The shear stress caused by the upper plate moving to the right is what ultimately drives the flow, not a pressure gradient like in flows through pressurized pipes. So we can deduce that the pressure should not vary in the y direction, and the partial p partial y term becomes 0. The Navier-Stokes equation in the z direction simplifies to negative density times the gravitational acceleration equals dp dz. And here we have replaced the partial derivatives with full derivatives because we've already determined the pressure is not a function of x or y, it's only a function of z. This is the same result for the pressure variation that we found in static fluids, which we called the hydrostatic pressure distribution. If we integrate this equation, we would find that the pressure increases linearly as we move from the top plate to the bottom plate. Now we have enough information to find how the velocity component v varies throughout the flow. V appears in the Navier-Stokes equations in the y direction. We can eliminate the absolute viscosity by dividing both sides of the equation by mu, and we can rewrite the partial derivatives as full derivatives since v only depends on z. Next, we multiply both sides of the equation by dz and integrate. The right side of the equation can be simplified to the integral of d dv dz, which is simply dv dz. On the left side of the equation, the integral of 0 dz is a constant, which we will call c1. We again multiply both sides by dz and integrate. After integration, the equation becomes c1 times z plus a constant, which we'll call c2, equals v. In order to determine the constants c1 and c2, we need to apply the boundary conditions at the top and bottom of the gap. The no-slip boundary condition means the speed of the fluid is 0 at the bottom plate, where z is equal to 0, and the speed of the fluid is capital U at the top plate, where z is equal to b. Applying the first boundary condition, v equals 0 at z equals 0, resulting in the constant c2 being 0. Applying the second boundary condition, v equals capital U at z equals b, and plugging in 0 for c2 results in c1 equaling u over b. Plugging in our values for c1 and c2 into the equation for v, we now have an expression for how v varies with z. It varies linearly, with a slope of u over b. Since v only varies in the z direction, the velocity profile is the same at every y location. One application of Couette flow is in the determination of the viscosity of liquids. One method for measuring the viscosity of liquids involves a cylindrical spindle rotating at a constant angular speed omega inside a cylindrical tube that contains a liquid. The outer tube is a fixed surface, while the spindle has a surface that moves at a constant speed. Here is a view from above showing the spindle radius r and the speed at the spindle surface, which is omega times r. If we take a closer look at the gap between the cylindrical tube wall and the spindle, we can see that the speed increases from 0 at the surface of the outer tube to omega times r at the surface of the spindle. A device called a rheometer measures the torque exerted on the spindle by fluid friction, which is the shear stress acting on the fluid. The strain rate of the liquid can be determined from the rotational speed. With this information, the rheometer can then calculate the viscosity of the liquid.